Okay, yeah. Good morning. Let me thank the organizers for inviting me. This is a great place and I've enjoyed it very much, my family as well. So yeah, thanks a lot. So I was asked to talk about phase transitions and also going a little bit beyond equilibrium and specifically in what can be done in ultracold atoms experimental systems. So I'm an experimentalist and I've worked most of my career with bosons, so I'll stick to bosons most of the time. I would say that fits the topic of the conference. Maybe I have one slide on fermions. But let me be clear that this is a super broad topic. I will not be able to cover everything. I will just go through the history of this and what are the main milestones, in my opinion, at least experimentally. So first of all, why would you care about looking at phase transitions with ultracold atoms? Well, simply because you have a very large degree of tunability of all possible parameters. You can change interactions, you can work with dimensionality, introduce disorder, shape whatever external potentials you want. And for example, do things that are not even thinkable in condensed matter systems, like for example, change dynamically the dimensionality of the system. You can do all these things with ultracold atoms, and this gives you an opportunity to explore these phase diagrams and look at different behaviors, emergent behaviors of these systems under a very controlled environment. So this is how typical experiment looks like. These are, I mean, I don't know if they're typical. These are the experiments I worked on during my career. So you should imagine, you know, a lot of optical tables, cables, optics everywhere, some sort of complicated vacuum systems, and then there is some cooling going on, and at the end you prepare your atoms into some well-controlled environment. So I would say the first phase transition that we have to think about is, you know, condensation. And this was achieved in 1995 in 2 groups and maybe 3. This wasn't clear at the time, then it was confirmed later. And the typical way in which we see this phase transition, this is a thermal phase transition, is we can look in time of flight at the cloud, we just release it from the trap, and we see that there is a thermal component, and then eventually cooling more and more, there is an occupation at momentum 0 that signals the phase transition has happened and there is coherence in the system. So I would say a clear way to investigate this phase transition can be found in this nice paper from 2000 in which the group of Hensch, they could take the BC, you have your BC in your trap, and basically make a double slit experiment with it. So you have a radio frequency that outcouples the atoms. So you have 2 streams of atoms coming down, matter waves, and these matter waves interfere with each other. And you can look at the interference fringes, and the visibility of the fringes gives you an idea of the G1 function, basically. And this G1 function, if you are at temperatures higher than the phase transition, goes to 0 at long range. So increasing the distance between the slits, the visibility goes away. While if you are at cold temperatures, the visibility stays high even for very large separation between the slits. And in a successive experiment in the Esslinger group, for example, they managed also to measure the critical exponent of the transition, basically repeating this experiment but more precisely, very close to the critical point, they could extract the critical exponent out. That matches with theory. There is some big error bar if you want, but you know, these things can be done with ultracold atoms, this kind of investigations. The error bars are typically due to the fact that this system is finite. That's something that is always a little bit of an issue when you want to compare to condensed matter systems. The sizes that we are talking about are not 10 to the 23, but they are maybe 10 to the 5 atoms, and there is finite size effects that you always have to manage a little bit. So let me talk a little bit about the tools that are available for experiments. And I would say the most important one is the ability to project potentials with arbitrary shapes, pretty much. And this is due to the fact that the atoms are some sort of polarizable objects. They have a polarizability, and we can write down a potential which is mainly dependent of the intensity of the light. So if you focus down a beam, we can make a trap that is sort of elongated for the atoms. If we cross two beams, we can make something a bit more spherical. And then we can also have things like standing waves, in which we have multiple welds in which we can put our atoms inside. And if we repeat this in 3D direction, we get a 3D optical lattice, cubic lattice in this case, but you can play with the angles and change the geometry. And this was described in this seminal paper, in which they pointed out that this system can really mimic the behavior of electrons in crystals by thinking about the atoms as the electrons hopping between welds of this light crystal. Another very important tool that I'm going to use is flashback resonance. So this gives us the ability to tune interactions. So at ultracold temperature, the only parameter that really defines the interaction is the scattering length. It's one single parameter, because the interaction only happens significantly in S-wave channel. And the scattering length parameterizes the strength of the interaction, basically. And you have a divergence in the scattering length every time a bound state enters your problem, basically, your scattering problem. And what we do typically is our atoms are at this energy and at some entrance channel. And then there is some closed channel, which is typically a different spin state, in which there is some bound state that we can tune. We can tune the position of the bound state very precisely, very close to the entrance threshold. And that causes a divergence in the scattering length, and we can use that to tune our system. We can go to strongly repulsive, strongly attractive. We can make the interaction zero. We have good control over this kind of thing. So first, quantum phase transition that has been investigated in this way is superfluid to multi-insulator phase transition. And you can see here, we basically have atoms in a lattice, and they can tunnel around. There is a tunneling term. And then if we find two particles at the same spot, we have an interaction energy that we have to pay. This Hamiltonian, this is the Bose-Hubbard Hamiltonian, has two main phases that it displays. Whenever the tunneling dominates, you have coherence across the system. You have a superfluid. And when the interaction dominates, you have a multi-insulator, so there are no fluctuations of number. The number of particles in each well is well defined. And you have loss of coherence. So that's the observation. You put your BC into the lattice, you ramp up the power, and then initially you see diffraction of the matter wave from the periodic structure. But you still have well-defined peaks in momentum space, which signal there is some sort of phase coherence. And then eventually, increasing more and more the lattice depth, at some point the interaction dominates, and you pass to the multi-insulator transition. So this is the way that it was first seen. Another very interesting tool we have available is we have the possibility to introduce disorder into the system, and this was observed what happens with matter waves inside this disorder system. In this couple papers here, you have different options on how to create the disorder. You can use speckles, or you can use so two lattices of different periods to mimic the effect of disorder. So each lattice well is a sort of random energy here. And in both cases, what you observe is that you insert some localized state, and then the state spreads for a while until it reaches some sort of exponentially localized shape. This is not really a phase transition, because we are in the non-interacting limit. It's just a behavior of the single particle wave functions. but it's an interesting tool that we are going to talk about, and we can see what happens when we start introducing interactions later. And this is the only fermionic slide. Another very important, phase transition scenario that has been investigated a lot in the past is the BCS-BEC crossover, where you have fermions. The fermions on the attractive side create Cooper pairs, and these Cooper pairs can support superfluidity below some temperature. And then if we go across the Feshbach resonance, we have the possibility to pair the pairs stronger and stronger until eventually they become molecules, and the molecules are bosons and they can condense. So you can really move around with basically even change the statistics that dominates the system in this ultracold systems. And this is an experiment showing that you have superfluidity, so you have quantized vortices all over the parameter range from the BCS to the BEC side. So in this case, they were able to stay below the critical temperature across the transition. And there are lots of other phase diagrams you can investigate with cold atoms. These are some that I investigated in my career. But just to have an example, you can look at what happens in higher dimensions with this order. You can have competition of different ordering possible. You can have magnetic phases. You can look at first order, second order phase transitions. So there is a lot of richness of this field. And as I said, I cannot cover everything. But what I want to talk about a little bit is, so we are still in the realm of equilibrium, so I'll talk about what we did in our system in Innsbruck. This is not really a phase transition, but it's still an equilibrium phenomenon that we can investigate with our system. So our system here is 1D tubes, so the same system that Isabelle or Jérôme was describing. We can use a Feshbach resonance to increase interactions, go to the very strongly interacting limit, Tonks-Girardot gas, and we can flip a single spin with a radio frequency and apply a force to it. So we can apply the force selectively only to the impurity and control the strength of the force quite precisely. So what happens in this case is that we can follow the ground state of the system and increasing the force more and more, climb this energy landscape. What happens here is that the system itself acquires anionic properties. So it has to be described in terms of anions at the underlying level. And you can see that by investigating the momentum distribution of the impurity itself. So if you look at the momentum distribution of the impurity, when you have zero momentum, then it's this bosonic thing that Jérôme derived at the board. And then increasing the momentum, you go towards some sort of asymmetric thing that is typical of an anionic system. And then eventually you can reach a fermionic momentum distribution when you reach KF. And this was predicted in this paper over here. And when Michel Patrizia came to us and told us about this story, we asked, okay, but why is there a connection between this impurity system and anions? And the answer was, well, I did the beta ansatz. Trust me, it's an exact result. So, well, we said, okay, interesting. Let's try to do it in the lab. So we tried it in the lab, and indeed, that's what you see. If at momentum zero, the momentum distribution of the impurity is peaked at zero, then it has a peak on one side, and then eventually it develops some sort of flat top, which is typical of a fermionic system. We have deviations because we have finite size effects. We cannot reproduce, divergences. But we think we understand what's going on. So, well, that was very interesting. We tried to figure out why that actually works. And this is my best explanation. I'll try to convince you that indeed there are some anionic properties here. So first of all, what we measure is the momentum distribution of the impurity. So the momentum distribution is the Fourier transform of the G1 function of the impurity. And the G1 function, what it's telling you is, okay, you have a single impurity in your system. kill it, and then create it at some other position. Okay, that's the operation that this thing is doing. Well, if you have to exchange two particles with the same spin, definitely you have bosonic exchange rules, so you would get a phase of 0. There is no way to get anyons out of that. But when you exchange a spin down with a spin up, you can get any sort of behavior. These are distinguishable particles, right? The idea here is that this move is the same as translating the whole system by a certain amount of sites, if you want, or like of positions. So you take the whole system, translate it, that's the same thing that this operator does. So because we are in an eigenstate of momentum, that means that this move has a well-defined phase attached to it, which is given by the momentum of the system. And so this phase factor is exactly what you need in order to generate the correct phase factor to put here, and then use a Jordan-Wigner transformation from bosonic operators to anionic operators. And then you see that, okay, this specific G1 function connects to the G1 function of an anionic system in this way. This only works for the G1 function, actually. So if you were to compute something else, for example, if you want to compute a two-body operator, then you need two impurities in the system, and then you could simulate the two-body correlation function of the anions, and so on. So there is a connection here, and there is an anionic behavior of the underlying system. Yeah, sure. Theta depends on momentum, basically, yeah. So it's the phase factor that you would pick under translation. Yeah, so momentum controls the statistical phase you get here. Does that? Okay. Okay, cool. And so we repeated the measurement, we did some more modeling, and we actually used a bunch of different models, an anionic Hubbard model, bosonic Hubbard model with spin, swap model. We came up with lots of different ways to model it. But actually, all of these models in the strongly interacting limit, and only in the strongly interacting limit, have this behavior that their underlying description is anionic, and you can see that in certain correlation functions of your spin-field system. And they reproduce the experiment, let's say, to a satisfactory result amount, and maybe the main deviations we see are for KF, which is the point where it's hardest to maintain adiabaticity, actually, to stay really close to the ground state. Okay, so now we talked about equilibrium. Let's try to go beyond equilibrium. I would, or are there questions before? Case, yeah, sure. Yeah, sure. This one, yeah. Yeah. Yeah, there are deviations, especially at the KF point. So when we try to make fermions, that's actually the hardest thing to do. And that's because there is a higher density of states there. So it's much harder to stay very close to the ground state, actually, for us experimentally. So we think it's a technical issue, yeah. Yeah.
What is the regime of the interaction of both gas with the ionicity, and how important it is to observe this?
Yeah, so at the theoretical level, the mapping to anions only works at infinite gamma, yeah. We work at gammas of 20, 30, so quite large, but of course it's finite. And it would be very interesting to develop this theory to the finite gamma region, but so far we didn't, figure out how. Because the mapping strictly is to hardcore anions. So we can only simulate strongly interacting anions. We basically can never have two anions at the same spot. That's sort of why this works. If the anions are soft, then there are deviations, of course, yeah. Yes.
Because this Fermi that it's with its KF, so it depends from Q to Q.
Yes. So.
Does it explain part of the deviation?
Yes, we believe so. So the issue is that The mapping between momentum and the statistical phase is basically momentum over kf is the statistical phase. But kf is not the same in all tubes. And so we believe that the deviation here can also be explained by the fact that we have different kfs into the system, and so it's hard to be really at the fermionic point. Would be nice to have a box and then try in that way to see if we have less deviations. Yeah.
But the theory is done for a single tube?
Yes. Yes, that's right. That's why it doesn't capture all the deviations, let's say here. There are some deviations due to adiabaticity that we can capture by doing finite time, but they are not enough to explain the data. Yeah. Good? Okay. All right, so I would break this beyond equilibrium, at least from my experimental perspective, into three categories. There is quenches, and in quenches you can look at relaxation, pre-thermalization, similar to what Nicolas was explaining yesterday, and try to look at new phases that emerge during the quench. Or you can drive your system, and typically driving the system, you can give new properties to your Hamiltonian. For example, you can look at topological phases. We've been looking at kick systems that I'm going to talk about a little bit. And then the final category is open systems. We don't really do that in cold atoms, but it's an interesting direction. Okay, so first thing, quenches. So you have your Hamiltonian, you take some parameter and jump it to a new value, you get new Hamiltonian. And the typical thing you expect is there is going to be some sort of transient behavior of observables, and then eventually they stabilize to some new effective equilibrium, let's call it. This is the kind of framework that you can use to describe the system, eigenstate thermalization hypothesis. So the idea is that at long time, everything will look more or less thermal. So all local observables will be well described by thermodynamical ensemble. And if you want, this is basically the ergodic hypothesis of Boltzmann, but in modern view. And but it's valid at the microscopic level. So all eigenstates of the system have this nice thermalization property, or nearly all. But the thing is that, well, this is an hypothesis for a reason, because it actually fails sometimes. And the cases in which it fails are kind of interesting to us. At least we want to understand what happens when this doesn't apply. So let me give an example. This is a famous paper where MBL, so many body localization, was observed in 2015. So what they do is they prepare a state very far from equilibrium, where you have occupation of every other lattice site. You have some tunneling, interactions, and disorder. And what they observe is that, maybe this is not so visible, but the imbalance, they measure the imbalance over time. The imbalance relaxes to some finite plateau. It doesn't go to zero. And that is a manifestation of the fact that there is no clear thermalization, at least for some time. I think if they continue the experiment, eventually the system would go to thermal equilibrium, but for a very long time, you can say that the system basically lacks thermalization. And this is called MBL, and MBL is a big topic, has been very controversial in the past few years, and so it's interesting to understand how it works, I would say. So my perspective on this is basically during the transient, you can have new phases for an extended amount of time. And this phenomenon is called pre-thermalization, as you've seen in Nicolas' talk yesterday. And it can happen in many different scenarios. You can have a system near integrability, for example, that will show pre-thermalization. Dynamical constraints, for example, you can have repulsively bound pairs show pre-thermalization behavior. Long-range interactions can give you that. So there are many reasons why you would see this phenomenon, but it's a very interesting and general phenomenon that you see in many systems. So, what we've done recently is an experiment that goes along these lines, trying to see what happens for these near integrable systems at long times, but not infinite times. So again, we have our 1D gases, no impurity this time, just bosons, and this is described by the Lieb-Lininger model. In particular, we were interested in what happens when you make the interaction parameter negative. So we are talking about attractive interactions. So there is a complicated, out of equilibrium phase diagram, if you want to call it that. And it looks like the following. So here you have repulsive interactions, and in the repulsive regime you have weakly interacting gases, or quasi-condensate if you want, and you have the Tonks regime, which is some sort of crossover between them. And if you take the Tonks regime and you quench it all over to very strong attractive interactions, you're going to find the super Tonks gas, which was discussed in this paper here. And this is basically the highest excited state of the attractive system, but it's nevertheless an eigenstate of the system. So if you really quench from the Tonks to the super Tonks, you're going to stay in that state for an extended period of time. That's a metastable state, if you want. If you go adiabatically through the zero crossing, which is sort of similar to what we are doing, you're going to go to the ideal gas. All the atoms are very close together. And then you're going to create what's called a giant cluster. So you have all the atoms in giant bound states, and or you can call it a soliton if you want. The problem is the density shoots up very high, and the system is lost over a very short period of time. So we cannot really observe the system in this state over here. So what we wanted to do is we wanted to use a finite speed ramp to go into a condition in which we have many beta strings, these are called. So beta strings are stable bound states of, you can find them in many integrable models, in which you have clusters of 2, 3, 4, 5, whatever, many particles. And these clusters are stable under collision. So whenever they collide, they don't mix up, they don't break, they stay together as a unique thing. So we wanted to see if we can get these beta strings, make them in the experiment, and measure their properties. So you can compute the binding energy of these strings. There is some universal formula that predicts it. So that's the thing that distinguishes them. They have binding energy. So we try to come up with some sort of protocol to measure that. And so the protocol goes like this. So you have your atoms in the harmonic trap. Hopefully you have some strings there. And then you first make a 1D expansion. So you keep the tubes on, but you flatten out the potential longitudinally. This way the strings expand and release their sort of kinetic energy. After that, we also switch off the transverse confinement. And at that point, the dimensionality of the system goes from 1D to 3D. The strings are not stable anymore, and they break apart, releasing their binding energy. And what you can do is you can look at the second moment of the cloud and look at its evolution in time. You're going to have two different behaviors, one with the 1D expansion and one with the 3D expansion. So when you look at the 3D expansion, you have kinetic energy and binding energy there. But when you look at the 1D expansion, you only have kinetic energy. So fitting this, we can extract two quantities, the release energy in 1D and the release energy in 3D, which you can plot here. So if we are on the repulsive side, the release energy in 1D and 3D tracks each other, at least within error bars. So we think there are no bound states there, as expected. But when we go to attractive interactions, we have a big difference between these two release energies. That is a direct indication of the average binding energy that we have in the system, basically. And we can measure that and look at the binding energy that we get. So we can compare this to the formula for different binding energies. So basically, this is saying, okay, if, for example, we make all bound states of the same size, what kind of binding energy would we expect? And the sort of number that fits here is about 7. So if all the particles were in bound states of 7 particles, then we would reproduce the same binding energy. The reality is we have a broad distribution. But this is to say that for sure there are larger than 7 aggregates. So that we have big bound states. It's not just couples and so on. Also, what we wanted to do is we wanted to measure some sort of thermodynamic properties, because we wanted to make sure that these pairs these strings are really in some sort of equilibrium, such that we can define their thermodynamic properties. And so I would say the most interesting property is called the contact. The contact is related to the 1/k4 dependence of the momentum distribution of these systems at large momentum. But to measure directly the momentum distribution, for us it was kind of tricky experimentally. We could never get a very nice fit to 1/k4. So we decided to measure it by measuring the internal energy of the system. So we have this method to extract the binding energy. We can extract all other energy terms and use the virial theorem to get a value for the contact. And you can see that the contact tracks the theory for the attractive side, and then for the repulsive side we have some deviation. Especially the deviation gets stronger and stronger when we push interactions, so stronger in modulus. Yeah? That's potential energy. This is full internal energy. It contains also binding energy. So everything, yeah.
Because time contact is related to derivative of energy versus one energy.
That's right.
How do you get this formula?
You get it in a system which is inhomogeneous. So you have a trap as well, and you have some sort of virial theorem that connects the average potential energy, internal energy, and so on to the derivative of the energy with respect to interaction.
If I would apply this formula to repulsive interaction regime,
Yeah.
then U is interaction energy, U is the total energy, EV is the potential energy, so I have just the kinetic energy, and contact is not equal to the kinetic energy.
We can look at it. I think it works, but we can discuss it later. But yeah, I see your point. I don't remember if there is a factor 2 somewhere, but I think there isn't, to be honest. But yeah, I can check it. Yeah, sure.
And this theory curve below, in what state is it?
Okay, so to compute this theory, we have the equilibrium state over here, and then on this side we have to sort of guess the distribution of strings, of course. And Alvise Bastianello figured out a way to do it. So basically, his idea is that at this point you are going to compute the entropy of the system at finite temperature. And with entropy arguments, you can predict the distribution of strings. Yeah? And once you have the distribution of strings, that cannot change anymore on this side. It can only change at the zero crossing. And we have been characterizing that distribution by comparing the momentum distribution with our experiment. And so that is the curve that you get from there.
So on the left, it's not the thermal equilibrium state.
It's a hydrodynamic. Yeah, it's a sort of hydrodynamic equilibrium, if you want. It's not the absolute thermal equilibrium, because if you wait too long for it to thermalize, then everything will be lost, basically. Yeah. It's a GG, exactly. Yeah. 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 It's a GG given the initial parameters of the protocol. Yeah. Okay. Thanks. Good. All right, so let's go now to the next topic, that is Floquet engineering. So another way to look at phases in ultracold atoms or in general is to start with some Hamiltonian that is simple enough, and then apply periodic driving. So this could be a force, it could be a laser, it could be anything that you start modulating periodically. So what happens after that is you have now a full Hamiltonian which is periodic in time, and you can write down the evolution operator of one period of the system, and this is a unitary operator. You can always write it in terms of some Hermitian operator. This Hermitian operator is the Floquet Hamiltonian. So the meaning of this Floquet Hamiltonian is the following. So if you have your drive versus time, you see what happens to your observables. The observables will evolve slowly in time with an evolution given by the Floquet Hamiltonian. And then they will have some micromotion on top of that. The micromotion can be small when you drive at high frequencies. So this is a way to engineer a new Hamiltonian by just driving your system. And this has been used a ton in ultracold atoms and also in other systems. It's a very flexible way to get a new Hamiltonian that you didn't know how to make, basically. So let me give you examples of how this has been used experimentally. So this is the first example I know about, at least, you take your atoms, they have some tunneling, you tilt the lattice. In this way, the tunneling is forbidden now because there is a large energy difference over here. And then you can shake your lattice at some frequency. When the frequency matches the energy difference, you can restore tunneling. So basically what they observed is that changing the frequency, when you hit the resonance, you are going to get superfluidity back. So you can change the phase of the system by changing the properties of the drive. Yep. What do you mean? It's periodic, yeah. No, it's periodic shaking, exactly, yeah. It's, that's the idea of Floquet drive. You always shake periodically, yeah. You can also do something more fancy, like, for example, in this experiment from the Esslinger group, where they started from an hexagonal lattice that they made with lasers, and then they shake the lattice positions in some sort of circular pattern, and this gives you next nearest neighbor tunneling terms, which have some sort of chirality to them. This maps to the Haldane model, and Haldane, when he came up with this model, said that nobody would actually realize it, but actually, well, it's possible to do this in ultracold atoms, and now in also other systems. And this basically has topological properties in the band structure, and they could measure the topological properties, basically the Chern number in these band structures as a function of parameters, and really see that it acquires topological properties in the appropriate regime. So this is a very powerful method. You can get new phases that are sort of interesting that you want to study. You can also go with this shaking to basically regimes in which you don't really have an effective Hamiltonian to speak about. You have some new phenomena that don't have equilibrium counterparts. So one example of this is you shake now not at very high frequency, but at sort of quasi-resonant, and you can get time crystal behavior. I'm cheating a little bit here. These two are not really cold atoms experiments, but still, I mean, that's the first manifestation of time crystals, if you want. I'm not going to go much into time crystals. Sorry about that. I want to talk about now low frequency driving. So you're driving, but you're driving a very slow frequency. Or you can think of kicking, right? Really, you kick now, and then you wait a long time, kick again, and so on. In this scenario, you talk about what's called the quantum kick rotor. And this can be described from the point of view on Anderson localization, but now in momentum space. And the way that this is observed is, for example, the first time in 1995, you can see that you start with a localized momentum distribution, and then over time, increasing the number of kicks, the momentum distribution broadens a little bit, but eventually reaches this sort of exponential shape, which is similar to what you get in Anderson localization. So we wanted to do the same experiment, but now with our atoms, and we wanted to especially think about what happens when you add interactions. So we can tune gamma to values of maybe 100 and so on, and we are interested in, okay, does this phenomenon survive in a strongly interacting limit? So we take our tubes, we have a lattice on it, and then we pulse the lattice on and off in a periodic fashion. These sort of time scales are of the order of maybe 50 microseconds, 60. We played a bit with it. So the idea we have behind it is, okay, for single particles, for weak interactions, we have, in the spatial case, we have Anderson localization. In momentum case, with the quantum kick rotor, we have dynamical localization. What happens when you go to the many-body limit? For Anderson localization, you get something that has been termed many-body localization. You can get Bose-Glass, depending if you are close to the ground state. It's not clear what you would get in the sort of dynamical case, and we name it many-body dynamical localization. I think it was named in a paper before us. So, but we wanted to see whether we could observe it experimentally. Yeah? So, and this is the observation. So you have your non-interacting system. You start with some momentum distribution that is close to zero. You have one kick, and you get momentum plus minus 2h per k. And then you keep kicking hundreds, thousands of kicks, and this momentum distribution really doesn't move much, which is a manifestation of this dynamical localization. When we have strong interactions, say gamma of 10, we see that there is a bit more dynamics initially. It broadens a bit, but then eventually it stops moving as well. So we can really tell that, okay, even this system with strong interactions reaches some sort of localization regime, which is a manifestation of this many-body localization. To make sure we are not making a mistake, we even tested what happens if you break this periodicity of the drive. So if you now start driving at random times, but with the same average energy. And in that case, no matter whether it's non-interacting or interacting, the momentum distribution flattens out very quickly over a few hundred kicks. So we believe that the localization we see, even in the interacting case, is a manifestation of interference processes going on in the system. But I would say I don't have very good modeling in mind for the strongly interacting regime. We have the ability to compute exact results for 2 or 3 particles now. So Matthias can do that. And well, you do see this phenomenon at the few particle level, but it would be nice to understand what happens at the many-body scale. Yeah? Okay, the last few things are about what can you think about doing in cross-platform synergies. In this conference, we have seen a lot of photonics going on, and things from the photonic point of view. And my point of view is that there are lots of opportunities in this talking to each other, because we really are working on very similar problems in the end of the day, but we have very different platforms that have strengths and weaknesses on both sides. So you can really come up with some ideas that are very hard to do in your platform, but maybe they are easy to do in atoms, or the other way around. So an example of this is looking at supersolidity. So I collaborated a little bit with the group in Lecce to think about supersolid in polariton systems. And so a supersolid is a phase of matter which has phase coherence and crystalline order, and you typically can see it by the momentum distribution. It acquires momenta at some strange places, which tells you that there is some sort of crystalline order going on. And this has to be gained from spontaneously by spontaneously breaking some continuous symmetries. So there are lots of experiments in the cold atoms side, and with different degrees of agreement in the community. So it's a debated topic, and we wanted to see if we could see something like that in polaritons. So when talking to the people in Lecce, they could actually do the experiment. And they could see really that, okay, they have now a polariton condensate that start to scatter in other modes, and these other modes really give you a modulation of the density. You can see that in situ. You can measure the G1 on the system, it's a very interesting perspective. You have new observables that are available to you that I wouldn't even think about in the cold atoms side. And so it has been a very interesting collaboration. I enjoyed it. And so this is the team, experimental team, the theory on the beta strings, anions, and MBDL. And let me thank everybody that contributed. And this is our group in Innsbruck. If you like the mountains, please consider. Yeah, thank you very much. Okay.